Hi class, we are going to be learning Unit 3.1 today, and that is about measurements and their uncertainty. So, starting off, we're going to define what a measurement is. It's defined as a quantity that has both a number and a unit. And so it's important to be able to make measurements and be able to decide whether a measurement is correct or not. This is a huge part of science. And so one of the main ways that we express our numbers is using scientific notation, which, if it's in scientific notation, it gives the number as a product of two numbers. And remember, product has to do with multiplication. So this is going to be given as a coefficient. Oops. And a 10 raised to a power. So an example would be 3.2 times 10 to the negative second. This would be in scientific notation, having the 3.2 being the coefficient, and the 10 is the 10, and then if you raise it to a power, that's our negative 2. Okay, then we have accuracy. So accuracy is the measure of how close a measurement comes to the actual or true value. And so if we're going to evaluate accuracy, we must take our measured value and compare it to the correct value. So this actual or true or correct value, there's a few ways to say it, but it all means the same thing, which is this value has been determined through multiple studies and comes from a reliable source. Okay, and then we have what's called precision, which is the measure of how close a series of measurements are to each other. So, to evaluate precision, you must compare values of two or more repeated measurements. And I'm sure some of you have seen this example before, but I think it's great. And it has to do with throwing darts at a dartboard. So, if we are accurate and precise, accurate would be our correct value, or our target is going to be the center. So All of these dots are in the center, as well as precise. They're all close to each other. And so if we skip over to the next one, again, they're all precise as they're close to each other, but they're not accurate because they're nowhere near our target. And then if we look at the third one, why this is accurate is because comparison to how far away they are from the bullseye, it's really not that far. But they're not precise because they're not all in the same vicinity. And then the last one is not accurate and not precise because they're not close to the bullseye and they're not close to each other. Okay, so let's talk about determining error. This comes from having these true values that we can look to. So we first have to define what is our accepted value. And like I was saying earlier, it's our correct value based on reliable references. Our experimental value are values we measure in lab. Our error is the difference between accepted and experimental values. So the error is the difference between these two values. So our percent error is the absolute value of the error divided by the accepted multiplied by 100%. So we have a formula for this. It would be experimental value minus the accepted. Because remember, if we are looking at the error is the difference. So that's how we get experimental minus accepted. So this is just the error. Now, we're taking the absolute value of it, and we're dividing this number by the accepted value. And then finally, multiplying by 100%. So, if I were to give you guys an example, I'm going to call it my boiling point example. So let's say we were trying to measure the boiling point of water. And what we measured was 98.9 degrees Celsius. And so our actual, which we know this from multiple studies and references. And so remember the actual, this can be the same thing as the correct or accepted. This is going to be 100.0% Celsius, which shouldn't be a surprise. So if we plug these values, because these are the only values we need, into the equation here, I'm going to call this equal to percent error. So if we calculate our percent error, we should get our experimental value, which is what we measured in lab, which is 98.9. We're subtracting it 100 from it because that's the accepted. We are taking the absolute value and we are dividing it by the actual again, so 100. and multiplying by 100%. So our percent error is equal to 1.1 degrees Celsius over 100 degrees Celsius times 100%, and you should get 1.1% as your answer.